Good afternoon, and welcome to Talks at Google in Cambridge, Massachusetts. Today, it's my great pleasure to introduce Juan Enriquez and Steve Gullans. Juan and Steve are here today to talk about their book, Evolving Ourselves, How Unnatural Selection and Nonrandom Mutation Are Changing Life on Earth, in which they state, "We are the primary drivers of change. We will directly and indirectly determine what lives, what dies, where, and when. We are in a different phase of evolution. The future of life is now in our hands." I don't know about you. I don't know if I'm quite ready for this, so I'm hoping the talk and the book will give us a way forward. Juan and Steve are co-founders of Excel Venture Management, which builds startups in synthetic biology, big data, and new genetic technologies. Juan is a TED All-Star. He chairs the Genetics Advisory Council at Harvard Medical School and was the founding director of Harvard Business School's Life Science Project. Steve was a professor at Harvard Medical School for 18 years. He has published more than 130 scientific papers in leading journals. He was elected a Fellow of the American Association for the Advancement of Science in 1998. Please join me in welcoming Juan Enriquez and Steve Gullans.
So what I think Steve and I would like to do today is give you a short introduction to the theme, and then Steve will say a few words, and then we'll chat and answer any questions you have. And I want to start with a truth and a dare around a very specific question, which is life's evolution. So let's just review Bio 101 for 2 or 3 minutes. This nice character, Charles Darwin, one of the greatest scientists and humanitarians ever born, came up with the notion that life evolves according to 2 rules. This is the first sheet of when he discovers or thinks of evolution. It's the first time he writes, "I think," and then draws a tree of life as to how things evolve. And this sheet was actually shown in Britain a few years ago. It was absolutely marvelous to see it. So how does life evolve? Well, life evolves according to natural selection. And what does natural selection mean? It means that very small variations in how a bird eats, what is a predator to a bird, what the climate is, what diseases are attacking it, can lead to big changes in a body. In this case, the Galapagos finches, depending on whether there was water or there wasn't water, would develop different kinds of beaks to have tougher seeds or to have smaller seeds. In a place like this, what you get is a whole lot of natural selection. So you get these little micro niches where all of these creatures learn how to survive, evolve within here, and basically compete against one another. And one of the ways in which they compete is they have their genes randomly mutating. So this is like a gene casino, where you throw the dice and the gene comes up with this letter, or this letter, or this letter, or this letter. And random mutation is exactly that, which is the reason why you can get cats with 23 toes. Right? It's a random process. Things appear and disappear. They don't have an order. There isn't a rhyme or a reason for it. And those changes which are beneficial means that that creature has children who have children who have children. This occurs in human beings as well. And sometimes it isn't pretty. Random mutation means you can have 6 digits or 7. And when you're thinking about the consequences of this, sometimes when you have random mutation, it actually looks like it makes sense. Maybe if you're a coder, you would want to have 6 fingers. Or of course, maybe if you're a baseball pitcher. So this is Unnatural Selection. His nickname was the octopus. He was born with 12 fingers, 12 toes, and he became the relief pitcher of the year in the year 2000. So it turns out that having 6 fingers in the right place allows you to do things as a pitcher that other people can't do. Random mutation works sometimes, and often it does not. So what are the drivers of evolution? What leads to changes in evolution? What creates evolutionary pressure? Well, you can have predators. If you have a change in predators, if you take yourself in or out of different food chains, that can lead to certain kinds of development. Changing your food, changing your microbes, your environment, your population. If you become domesticated, if you change your labor or exercise regime, you can have changes. And the key question here is, how many of these factors do you suppose have changed for human beings in the last century or two? Do you think we have changed the predators? Are we still subject to grizzly bears and mountain lions? Have we changed our food? Have we changed the kinds of microbes that attack us as we take out smallpox and polio? Have we changed our environment just a little bit? Have we increased our population? Have we become a different type of domesticated species? And the jobs we have, are they mostly outdoors and hard work, or are they a different kind of job? So as you go through these questions, let's try a mind experiment. Let's drop Charles Darwin in the middle of Trafalgar Square yesterday. So after the initial brutal disorientation, after trying to figure out what all these cars are, he'd begin to look around, and this is what he'd see. And he'd recognize most of these buildings. And then in his little careful way, he'd take out his notebook and start taking notes, and what would he see? Well, the first thing he'd see is, boy, human beings have gotten awfully big, because now there's about 1.46 billion overweight adults wandering around. And of course, all of you saw this in your last cross-country trip when the middle seat was occupied by somebody who liked your seat as well. House cats, house dogs have gotten fat. The leading cause of insurance claims today on pets is complications related to obesity. The interesting thing is it's not just domesticated pets and humans that are getting fat. It turns out a lot of wild animals are getting fat. So in fact, there's at least 12 species of animals that are sitting out there that are getting fat, which you wouldn't expect. Lab rats are getting fat, and all of you know that when you run an experiment, you don't want to have changes in the variables. So it's very odd that lab monkeys, lab rats are getting fat. It's even stranger that wild horses that eat grass are getting fat. So it's not just Twinkies, it's not just soft drinks out there. There's something else happening in this environment that is leading to obesity. A couple of potential causes of this. The subtherapeutic use of antibiotics. We're using a lot of antibiotics on farms. We don't use them to cure disease. We use them because when you feed small amounts of antibiotics to animals, you get weight gain. Perhaps because you break some of the microbes in the stomach, and therefore you absorb more nutrients. As we put more and more antibiotics into the environment, and a whole lot more antibiotics are being used for food promotion, spraying it on fruit trees, putting it into chickens, putting it into pigs, then we're putting a whole lot of antibiotics into the environment. Second thing that's happening, which is interesting, is there's a whole class of chemicals called obesogens that tend to promote weight gain. So some of the chemicals in our everyday products make it easier for fat to accumulate in bodies. And we're seeing that effect not just on humans, we're seeing it across a series of animals. Second thing that's happening, or second thing Darwin would note, is we've become a whole lot weaker. So a couple of centuries ago, most people worked hard labor someplace. They were working on assembly lines, they were working on industrial lines, they were working on farms. They were doing pretty brutal work. And today, of course, we've become coders, we've become office people. And sometimes if we work out enough, you don't have the same effect, but for most of us, we are quite weak compared to folks 150 years ago. Third thing you notice, boy, has this population gotten old. Where are all the kids? There's so many old people walking around Trafalgar Square. And of course, if there was a race coming by, then you'd notice that there were 75-year-olds that were beating the younger people as they raced by in a half marathon. If you tabulate these and many other changes, what you find is in a very short period of time, in less than 150 years, you get really substantial changes in the morphology of the human body. If you saw this in any other animal, you would ask the question, is this a new species? And of course, when you ask that of human beings, you begin to get some visions that perhaps tell you not only is it heading in a different direction, but it might also be mutating. That leads to an interesting question. Were this guy writing today, if he were walking through the labs here in Cambridge, if he knew what we now know about molecular biology, would he be writing the same books? And the answer is, it's not just the morphology that's changing, so are the basic drivers of evolution. Let me explain that. For 4 billion years, nature ran the show. So nature was in charge. Okay? And how was nature in charge? You had natural selection. So survival of the fittest, and you'd have this cycle, and what would happen is you'd get these random mutations, and the random mutations would allow something that was on the verge of going extinct to have one version that may have adapted better to that environment, that would then survive, have a lot of kids, thrive in that niche. And it was this cycle of natural selection, random mutation, that determined what lived and died on Earth for close to 4 billion years. Over the last century, what's ended up happening is humans now run half the show. So humans determine what lives and dies on at least half of the surface of the Earth and half of the oceans of the Earth. And what that means is that unnatural selection and non-random mutation are beginning to determine what lives and dies, begin to drive evolution. Let me explain this. So for at least half of life on Earth, unnatural selection looks something like this. This is not what you would find if nature were running the show, okay? You do not find cattle. You find buffalo, but not cattle on these kinds of plains. You do not find these kinds of plants on these plains. You do not find human beings traditionally on these kinds of plains, and you certainly didn't find horses on the American plains being ridden by humans. You want to be even more extreme, just walk into a cornfield. What lives and dies in a cornfield has nothing to do with what nature would select. It has everything to do with what we want. We don't want birds eating the seed. We don't want weeds eating over here. We don't want any plants that aren't corn. We want corn, and we want it for miles, and we want it in orderly rows. That is not natural selection. That is human selection, and our rural landscape absolutely reflects this. So as you go out and you look at not only what does the landscape look like, but what grows there, we have so thoroughly changed nature to our purposes that wild mustard weed, something that looks like this, sometimes has its flowers suppressed. When you suppress the flowers of mustard weed, you get broccoli. Otherwise, you wouldn't get broccoli. When you have bigger leaves in the mustard weed, then you get kale, which you can buy downstairs in your cafe. When you sterilize mustard flowers, then you get cauliflower. So you can take this weed, and you can change the genes or the physical characteristics or the way it grows and evolve it to suit your purposes, your size, your color, your desire, your productivity. But that has nothing to do with random selection, and that has nothing to do with random mutation. That has to do with our breeding, hybridizing, guiding what we want these plants to do. And of course, we've been doing this with ourselves. We've gone from being primarily a rural species that traditionally, for over 90% of its history, lived in groups of about 150 and separated every time it got above 150 into these large urban communities. And what's happened in the last decade or two is we've gone from being a majority rural species living in small towns and villages to being a majority urban species. And some of these urban areas are getting quite large. To be able to live in communities like this, you have to change the animal. If you take a wild animal and you change the environment, it can have some rapid evolutionary pressure, and the same thing is happening with human beings. Let me give you a sense of how fast this is happening. So China, in 3 years, used 150% more cement than the US did in a century. China, in the next couple of decades, is going to build 30 cities that are as large as some of the 30 largest cities on the planet. This is an enormous process of urbanization, and something similar is going to happen in India. To domesticate ourselves, to domesticate our pets, what we have to do is we have to take species, animals that normally don't live together, de-wild them, teach them to live with those that are traditionally not their friends, and teach them a series of rules. Because if you're going to live in a very tight-knit environment, maybe you can tolerate a couple of psychopaths on the Mongolian plain if you're going out as Genghis Khan to conquer the continent. You've got the whole continent in front of you. But if you have 5 psychopaths in your 60-story building in New York or Hong Kong or London, that is a very bad thing to do. So what you end up doing is you end up domesticating not just dogs, not just cats, but also humans. And this process of domestication has been going on for a long time. Those places that did not have a state, did not have dictators, did not have kings, were incredibly dangerous places to live in. So if you look at non-state societies on the top, your chances of being violently killed throughout your lifetime were astronomical, even when compared with ancient Mexico, the first line on the bottom. So you take the Mayas, you take the Aztecs, you take the Toltecs, you take all these people who would sacrifice thousands and bathe the pyramids, they were still a whole lot less violent because it was a state-sanctioned violence than were societies that were not organized into state societies. Then by the time you get to France in the 19th century, the violence has come down. By the time you get to Western Europe, US, and the world in 2007 at the very bottom. So the world, despite what you're reading, which is horrendous, in Congo, in Mexico, in ISIS, in a whole series of places, is a whole lot more peaceful today than it's ever been. All you have to do is go to any museum. So if you go down the street here to the Museum of Fine Arts, and you look at the paintings from the 1400s and the 1500s, what you're going to see is that the entertainment on Saturdays was to see if you could take somebody and burn them to death while you were torturing them, while you were whipping them, while you were stabbing them, before you dismembered them. And that was kind of common entertainment, right? Please don't do this because we will hurt you and we will make it last for a long time, and we will make an example out of you. As we decided that these types of things were not things we wanted to see, and we did not want our kids to see it in the main square on Saturdays, what started happening is we began domesticating violence. So if you were a European New Englander in 1650, you were 8 times more likely to die in a violent incident than you were by 1800. Right? This is not applicable to African Americans, it's not applicable to Hispanics, but if you were a white New Englander, this was a really, really dangerous place in 1650, and it was far less dangerous by 1800. For other groups, it took longer. So we continued to treat groups of the population in absolutely barbaric ways through Darwin's time. If you were an escaped slave, this is part of what would happen to you, and you'd be left to hang so that everybody could see you suffer for days. We do not consider this rational, reasonable behavior here or anywhere. So as we go out and we domesticate ourselves, part of what we're seeing is we're seeing this collapse in violence. And this collapse in violence is happening almost everywhere. If you look at the G5, or if you look at Boston. When I was in college, the old combat zone was not a place where you wanted to get off the Trombley bus. Today it's the funky theater district. Near your offices in New York, Chelsea was not the nicest place to be. 42nd Street was a very dangerous street. Today it looks like Disneyland. So as we go through this process of rapid domestication, the other thing that's happened is we've been able to create wealth on an absolutely unprecedented level. For most of human history, we could not generate enough calories to keep everybody alive. We had huge starvation incidents, and we had a huge incidence of malnutrition. Today in Mexico, the incidence of obesity is greater than the incidence of malnutrition. And that's certainly true of many other countries. So what we're doing these days, through businesses that are high-tech businesses, through a whole series of educational structures, by educating women, by educating our kids, is we're able to generate enormous output per person, which is generating an enormous amount of GDP for the world as a whole. And the other thing that's happened in this process of domestication is nature, this big, tough, survival of the fittest, select the people who are going to survive, has all of a sudden become this funky little thing where we go out on a weekend and we put on our little Patagonia jacket and we put on our little fluorescent things and we go for a hike in nature. We did not used to do that, okay? The edge of the forest was a dangerous place. It's a place where you could become a part of the food chain because there were bears, because there were mountain lions, because there were robbers, because there was disease, because there were a whole series of reasons why most people for most of their lives stuck very close to home. Because nature was not a place to go and play. Nature was a place to be afraid of. And today, nature has become our playground. We go out on the weekend. I'm going for a hike in the forest. Nature has become a plaything for most of us. That is true even of most violent weather events. As we get better at predicting these things, one of the things that happens is every single decade, the deaths per year and the death rates per year have gone through the floor. As we get better at predicting hurricanes, what you say is, be careful, there's a hurricane coming. Evacuate, put your things up, get your flashlights, get your water, bring the kids indoors. As you get tornadoes, tornado warning systems are getting better and better. Now, this is not true for everything. It is not true for earthquakes yet, which also can be important for the high-tech industry. But on the whole, your chances of dying due to an extreme weather event are dropping and dropping and dropping as we domesticate this. So that's what unnatural selection looks like. Now let's talk about non-random mutation, because that is also a big driver of evolution. Berg, Boyer, and Cohen. It sounds like a law firm, but what these three characters did is they figured out how to do what all of you do, which is how to code, except they weren't using digital code, they were using life code. So these three characters figured out you can insert genes, you can move genes, you can do biotechnology. They built some huge companies coming out of this database, and they built a huge industry, and they began to change life based on this stuff. What that means is nature goes from operating on a strictly random mutation basis to a non-random mutation basis. And if I were to choose to be mildly provocative, I'd say we're even heading towards intelligent design. What does this mean? It means if you spend about $40 million, not billion, and you go out and work for 4 or 5 years, you can take a picture that looks like this. And I know you're wildly excited by this picture, so was I. So what is this picture? Well, this picture is the first bacterial cell controlled by a chemically synthesized genome, which means Craig Venter and Ham Smith and John Glass and a team was able to go out and code from scratch the operating system for a cell. And that means that cells become programmable. In the same way as you can program an Intel chip and say to the chip, please give me a map, please give me a direction, please give me a review of a restaurant, please give me a accounting, please research this, please code that. As long as it's in ones and zeros, it really doesn't matter what's moving through that chip. Well, what this little cell means is you can begin to code this chip to execute various functions. Out of this little discovery, we created a company called Synthetic Genomics. And what Synthetic Genomics does is it tries to make fuels for one of the largest fuel companies in the world. It makes chemicals for one of the largest chemical companies in the world. It makes food for one of the largest food companies in the world. It stores information on an absolutely massive basis. It humanizes pig organs so they can be transplanted into humans. And the kinds of coders that you're going to see in a room like this in a decade, 2 decades, 3 decades are increasingly going to be people who are moving between digital code and life code. Because life code is a very powerful system. One big difference between what coders do today and what coders do tomorrow is this software builds its own hardware. No matter how you program a computer, you're not going to find 1,000 computers in the morning. But if I were to ask you who is the most published author across all time, in all editions, in all languages, most of you probably wouldn't tell me it's George Church, who's a Harvard Medical School professor, who figured out that anything you can code in ATCG, the 4 letters of DNA, you can code in ones and zeros. So you can say A equals 0, 0, T equals 0, 1, G equals 1, 0, and C equals 1, 1. And digital code becomes interchangeable with life code. It becomes bioinformatics. And anything you can write in digital code, you can now write in life code. With the difference that this software makes its own hardware, which means he put his book into a bacteria that reproduced 1 billion times, and his first edition was 1 billion copies. You can store almost the entire world's information and database in a glass of water if you're storing it in DNA. So as this stuff moves forward, instead of having random mutation, and this is a slide by Drew Endy where he describes this process, random mutation takes the first line of code that you see up there. So a creature is born, a creature has no eyes, it develops one eye, has a few generations with one eye, it tries 2 eyes are better, then it goes back to 1 eye because it's a random mutation. Then some of the 1 eye survive, but the 2 eye do even better. And then it starts developing other facial features, but this is a very long time scale. You're looking at centuries or millennia for these things to take place. When we start controlling and making the stuff non-random, what we do is we go out, we find a mutation we like, we sequence it, we put it in ATCGs, put it in digital code, synthesize it, and put it in another organism. And then things have 2 eyes from then on. So it goes from being a random process into being a very directed process, and this shortens the time scale brutally. It means evolution takes place according to our will, our design, in a short period of time. That's why you're having debates over the past month over a technology called Crispr. So Crispr is something that was developed very close to here in Cambridge, Mass. It was developed first out of yogurt, actually, at Danone. But there's 3 centers that are pushing CRISPR very hard. And what that means is, instead of coding individually line by line, you can take huge blocks of code and take them from here and insert them over here, and take them from here and insert them over here, which means you can have a very, very rapid evolution of creatures and species and bacteria and plants and animals in a very directed basis. And high school kids and college kids can use this technology. And that's leading some scientists to ask the question, what happens if we start editing humans? So within the past month, you've seen letters like this and reactions like this, because among other things, sometime this year, the first human being born to 3 parents will be born in Great Britain, genetically. Why is that happening? Because some children are born with a random mutation that is sometimes deadly, sometimes it's inherited, but the consequences are horrendous. Basically, it's like having cells without a battery, and you get all kinds of just horrible medical side effects and death early for these children. So what are they doing? They're taking the cells from a third human being and inserting it into the original egg and changing the gene code of that. That has a couple of implications. Implication number 1, first human being born to 3 genetic parents. Implication number 2, that child, if he or she has babies, will pass on this mutation to their children. So you're not just editing the individual, you're editing the subsequent copies of that individual. And that's a different gig from just editing individuals. Some people say this is moving too fast. Well, it is moving fast, in part because of the zip code. Because every year, MIT hosts the International Genetically Engineered Machine Competition. And you have a bunch of coders who come in here, not with computers, but with living things that they've been coding over the last year. And they show each other what they've made. So some of these kids are coding bacteria so that they have a 100 megapixel resolution on photographs, about 10 times a high-end digital camera. Some kids are coding yogurt so that it substitutes for part of your kidney. Some kids are trying to make television plasma screens that are alive. And the Tokyo team came in and made 4 very simple changes. They came in and they said, okay, we're going to take a basic bacteria, we're going to make sure it doesn't burn with radiation, we're going to make sure it doesn't freeze, we're going to make sure that it oxidizes, and we're going to make sure that the thing doesn't sunburn. Technically, that's not that big a deal, right? Those are just 4 mutations inserted into a bacterium. But when you ask these kids, why are you doing this stuff? The ambition was breathtaking, because what they wanted to do was to stick the stuff in the nose cones of rockets, shoot them at the Martian ice caps, have the bacteria land, survive, oxidize, create an atmosphere that would terraform Mars. So the implication of software that builds its own hardware can be significant. And in the same way as you used to have internet cafes, in the same way as you used to have these little hacker clubs, today you've got these biocurious clubs, where for $150 you have access to all the machines necessary to begin to play with gene code. So here's the truth in this talk. The truth is, it's not the religious fundamentalists that are slowly killing Darwin. It's scientists. And they're slowly killing Darwin not because he's wrong. Darwin is absolutely right, and he got the rules right. And that's the way life operated for 4 billion years. But what we've got now is we've got a parallel evolutionary system that's operating on a different logic. And that different logic of what lives and what dies depends on what human beings want to decide to live or die, not what nature is deciding. Humans are directly and deliberately beginning to take control of evolution. And as they do so, a part of evolution is now being driven by unnatural selection and nonrandom mutation. And that has a whole series of implications for life. So here's the dare in this talk. Dare we take control of evolution and deal with its symptoms and consequences? And if you take that question seriously, there isn't anything on Earth that doesn't change. You're going to see changes in diseases we get. You're going to see changes in how long we live. You're going to see changes in the types of companies we build. You're going to see changes in what we grow, in what lives, and what dies, in new species coming up, perhaps in extinct species being resurrected, and a whole series of species disappearing. There are symptoms and there are consequences of this rapid evolution, and we should be asking ourselves if we are going to redesign bacteria, plants, animals, and ourselves. What do we want to ask archaeologists, or what do we want archaeologists to find in 1,000 years, and 10,000 years, and 100,000 years? Because we now have the power, we're beginning to have the power, to answer these questions. Let me close with one last thought, because you're all coders. There are decades where nothing happens, and then there are weeks where decades happen. And that just happened over the last year. So for 4 billion years, as far as we know, most life was coded in DNA. Most life was coded in these 4 bands of ATCG that are inside DNA. So you knew what the code was. You knew how to write it. But as of the last year, because of this lab, you now have ATXY. What does that mean? That means that now you have a system of heredity that passes on life code that is written in chemicals that are different from what life on this planet has been written for the last 4 billion years. In theory, what this means is you could create a set of plants that would be immune to most or all viruses, most or all bacteria. A completely parallel evolutionary tree that wouldn't breed with this evolutionary tree. You'd watch evolution happen in a completely different way. Long term, it means we're going to be able to code for wholly different chemical environments. So if we wanted, for instance, to live in a place that was very different from Earth, this begins to give you a sense that maybe you couldn't design something that looks like humans, but maybe you could design bacteria for that place. Maybe you could even design basic plants for something that looks like that. And that is why we all have to pay attention to how we're evolving ourselves and what we're going to do with this newfound power. And now I'll let Steve make some comments.
I'm going to follow up with just a few minutes to try to personalize a little bit. And in terms of what does this mean to you? It sounds like a very big idea, a lot of ideas. And how does it actually relevant to getting up and walking out and thinking about next week, next month, next year for you? About a year and a half ago, while writing the book, Juan and I were living in this bizarre world that you've just seen, trying to pull pieces of it together. My wife and I were sitting there when we got a Skype call from my daughter and my son-in-law announcing that my daughter was pregnant. And with that, I panicked because I suddenly knew too much about evolution at a time when I had no idea where my DNA was headed, and I needed to come to grips with this. I spent furious weeks actually creating a new chapter. It's called A Perfectly Modern Pregnancy, as you'll see in the book. And what's interesting about this is you and I and the people in this room live in a very different world than people in Darwin's day. We're educated. We have perfect indoor climate every day. We have modern medicine. We are smarter. We have all of these great attributes. In fact, life is pretty good for us. So why would these scenarios about evolution changing have an impact on us in any way, shape, or form that we would really care about? Well, this is when I bumped into this world called transgenerational inheritance, or transgenerational heritability. It turns out that every mother and father at the earliest ages, in fact in utero, are going to become parents someday, and their sperm and eggs are carrying on the surface little listening receptors, listening to the world at large, so that the next generation, once you become pregnant, is informed. It's times of famine, it's times of plenty. There's a bacterial infection out there, there's violence going on. And so in fact, the next generation is being prepared without it having even been conceived or in utero for what it's about to come into. And we've seen this over the last about 100 years of studies, very rarely in humans. At times of war, we find famine is actually propagated. Famine in parents or parents-to-be is propagated as metabolic, heart disease, and schizophrenia 2 generations later, even though everybody in between, including the original grandparents, had enough food. There's also good scenarios where people have actually good exposures to life and actually have very good outcomes. So in fact, there is a memory of the life we're living, the memory of the life our parents lived, and a memory of our grandparents' lives that resides within us, that lives every day. What's the good news? We live great lives, by and large, compared to what happened before. But we also see, in other words, we're brighter, we have less disease in general. We have actually fewer headaches, but we're also seeing rises in a number of conditions, autism, obesity, and everything else. Nobody can find the genes. We discussed this in the book. You generally find genes that account for about 5%. But meanwhile, this nature-nurture is locked in synchrony to figure out how to take care of the next generation in the world to come. So as my daughter was having the baby, I was going through month by month, looking at what food she was eating, what vitamins were going on, the recent peanut allergy thing that came out. I was shipping her peanuts every week to eat when she was pregnant. She's going, what's this about? But I was seeing abstracts in the literature about exposure to antigens. So as we live over the next few years, and my daughter came out with a beautiful pregnancy. You actually saw my granddaughter in the pictures of the mutated chicken. That was her Halloween costume this last year. Although we're still curious about my son-in-law's DNA, to be honest. But frankly, the world at large for my granddaughter is going to be beautiful, but we have many things to learn in the near term. And in fact, just one final note about what is it that is coming. We all have DNA, we all understand DNA, it's the be-all and end-all. It turns out in a computer context, that's like the operating system. It virtually never changes. It's the most boring part of our biology. In fact, we have 4 genomes that we're all born with, and one keeps us alive, keeps us reproducing, that's our DNA. We're all 99.9% identical, otherwise we wouldn't survive as a species. The other 2 are your epigenome, which is switches on your DNA that get flipped. This is what happens when the famine comes. This is what happens when the violence changes, when the weather comes. When you're deprived of love as a child, why does it turn into heart disease when you're 80? These are these switches getting flipped. That's a very important genome, and the epigenetic code has not been uncovered. And that's like having programs like Word or any of the applications. The next one is your microbes in your body. we're now finding microbes that are providing 30% of the nutrients and toxins in our body. Every day we are carrying these around. They've changed completely in the last 50 years because of antibiotics, because of the food we eat. We are totally engineering the microbes. This is like little apps. They're actually sitting on top of our genome, changing little applications every day, and they will be engineered into functional foods in the next decade. And finally, there's viruses that live in us. At the DNA level, they're tenfold more abundant than bacteria, which are tenfold more abundant than our human cells. This is the dark matter of humanity right now. These viruses that live in us, we do not understand. They're driving our evolution, they're driving our nature every day, and there's more to come. But what I can say is if you have a healthy, happy life and follow the basic rules that you hear every week from your doctor, things are going to work out pretty well. And with that, I'll say thank you very much. Hope you read our book.
Questions, comments, rebuttals, please.
Isn't this sort of the logical endpoint of any sort of self-replicating system given that time and therefore perfectly natural? I mean,
There's a whole debate as to what's actually natural. So when you go to a organic food market on a weekend and you go shopping for all these wonderful organic things, all natural corn used to be called simple, and it was smaller than your thumbnail, and it had multicolored grains, and they didn't fall off easily. All natural tomatoes used to be green, tiny, and poisonous. Potatoes used to be poisonous. So what we've been doing for a long period of time is to evolve things to our purposes and select things to our purposes. Now, what we've been doing lately is we've been doing things that are, I think, far more extreme. Now, on the one hand, you could say, well, that humans are just a evolutionary system and they're a natural outgrowth of that evolutionary system. Yeah, but I think it's important to make a distinction between what we're doing, how we're engineering stuff, and how things worked in Darwin's time. Because if you don't do that, then what ends up happening is you don't take responsibility for what you're doing. You kind of say, this stuff just happens, it's all natural, que sera, sera, and it's not que sera, sera, right? It's, I choose to do this at this point to this species. And that has real consequences. And if we want to continue to have the power we have and continue to deploy it, we better recognize that this is a break point in evolution.
And we're just following up on what Darwin said. He attributed natural selection to anything that was effectively not driven by humans. He used terms like artificial selection, human selection, because he understood animal breeding, he understood plant breeding. But he said these are two different worlds. And from his perspective, 150 years ago, nature will always win. That's one of the things that's in debate now.
I guess I can't get a sense for whether or not you guys think this is a good thing or a bad thing that we have the ability to do this.
Well, that's up to all of us. We tend to be optimistic curmudgeons, but it's what we choose, right? It's not just, oh my goodness, this happened to me. There are consequences to choices.
True.
So, what would happen if we use this technology to engineer our own selves to live forever? And then we don't care about future generations because we'll just stop procreating. And, isn't that a possible scenario?
It's certainly a possible scenario. I mean, the way we see new technologies in terms of healthcare kinds of systems like we're talking about here is, first you do the obvious. You take on tragic neonatal diseases with children born with genetic problems and things like that. In fact, the first gene therapy was just approved 3 years ago for an inborn error of metabolism for kids. From there, you move into older people like cancers and things like that. And that's where these technologies are getting deployed right now. And we're at the very dawn of these technologies having an impact. But in other aspects of other things we've seen in healthcare technologies, it's not very long before they move into beauty. For example, you have LASIK surgery because people don't want to have glasses. You have Botox. You have all of these things that were initially designed to treat diseases are actually being treated for other things. And so aging and beauty, and then sports comes in with the growth factors and things like that.
And you can give people blood serum of younger people.
Absolutely. And it's
And also your own. You can donate now.
there are many ways, and so everybody, so you go in there. I want health, and then I want age to not age, then I want to live forever. Is basically what it comes down to, and people appear to continue to pursue this. Now, the technologies that are going to come to be used are going to be more powerful, and it really comes first down to safety and cost. When will they be safe and cost effective? And at that point, well, we need to have a debate now, but at that point, the rules will probably change in terms of how societies look at it, just as we have rules around taking vaccines for the measles. It's now viewed as a personal choice in many parts of this country, whether you actually get the measles or not.
But I would argue that it's a personal choice if you want to live forever versus, you know, and not have any children versus having children and then deciding to make room for them on this planet.
Let's see, even your question, which is an interesting question, we've decoupled sex from time. So for our grandparents, it was basically marriage and kids a few months later.
Right.
And today we choose,
Not to.
you know, I'm not going to have kids for the next 3 years, or even if I'm going to have kids, I can have kids and freeze the sperm, freeze the eggs, freeze the fertilized eggs, put them into a surrogate mother, and have a child that is born years after conception. And now you're beginning to say, not only can I do that, but I can begin to do some diagnostics on the genes, or I can change part of the genes, right? So there's a whole series of really important questions that are going to change and challenge us and our kids in ways that we just can't imagine. Now, none of us are going to live forever. But we did double the lifespan in the last century, and we're likely to double the lifespan again in this century. And after that, as these things accelerate, right now we're adding about 1 year of life per every 10 years we live, right? And as this stuff accelerates, if life or consciousness becomes downloadable, then you get some very interesting effects.
Devil's advocate here.
The curmudgeon.
So we all know one of the most pressing concerns about all of this is an unlucky accident, right? What was that science fiction short story about Ice 9? I think it was Ray Bradbury or something, where it got dropped in the sink and the world froze. Okay, so
Vonnegut.
yeah, Cat's Cradle by Kurt Vonnegut. Okay.
Yep.
So what if we, you know, accidentally mutate or deliberately mutate a virus or bacteria, something small, most likely, that's really good at what it does, and it doesn't like, well, maybe we're food, right? And we're kind of a monoculture, right? So you must get this question all the time, don't you? And how do you answer that?
I turn to Steve and I say, go ahead, Steve.
We deal with dystopian futures all the time and stuff like this, and it's been, you know, if you go back to Methuselah, it's the idea that everything is coming to an end because of some new technology is not unusual. That's a pretty typical thing. To think that this is more powerful, at least today, than anything we've ever seen before, in some ways is true, but in many ways is not true, because it underestimates what we as a human species, both technically and I think morally, are going to be able to do. And that's because I'm working from an optimistic perspective. I think our ability to control these things is better than people appreciate.
And the flip side is we're also, you know, we're building things like a digital biological converter that will allow you to take a small vial of flu, sequence it, put it into a computer program that compares it to every known flu, design a vaccine, beam that up to an airplane, and print a vaccine before that airplane lands. So as we meet new challenges, as things evolve, as things get created, I'm pretty optimistic we're going to be able to go after a whole series of things. I think we'll be able to take out cancer probably in the next decade or two, most cancers. I think after that, you've got to take out Alzheimer's and Parkinson's, and once you do that, then one of the leading causes of accidents in the world, with some research that Steve did, is accidents. Right? It's falling down staircases. It's getting tangled in bed sheets. That's what starts to kill a lot of people, because we've gotten rid of most of the top 10 killers from Darwin's time. You look at top 10 causes of death, 1850. We've gotten rid of almost all.
I very earnestly hope you're right about that.
So do I. And if we're not right, I'll give you a really expensive bottle of wine.
So you made a lot of comparisons to computer science, and I think one thing that has really accelerated the speed at which we can write computer code is that we went from punch cards to assembly language to Java. And now, or Python, right? And you can just like download libraries that do the common things that you need to do, and you're writing your code at a much higher level. Are there initiatives to do this on a biological scale as well?
There's lots of initiatives, both in terms of designing things and building things. I mean, there's a DY, and the first point I should make is like coding, you can learn it as a child. Manipulating genes, you can learn as a child. These are basically recipes you can do in your kitchen. And you can go to the internet and find out what we're talking about bacteria that grow naturally everywhere in your dirt, on your kitchen counter, or anything. And learning how to manipulate those is not a huge technical change. We've now been operating at a level of basically ones and zeros with ATCG. And the higher level programming languages effectively are coming out right now. These are some of the companies we're seeing, where you could actually take a metabolic pathway and slot that in, and you can take a sensing pathway and put that in, and then the synthetic systems to build these things, computerized, roboticized events, are actually going to allow you to assemble things in
at a higher level.
And there's libraries of functional units. These are called biobricks. Is actually the name was made up here with Drew Endy and people at MIT. Biobricks. These are actually functional units from different species that are stored. And they actually give you a 3x5 card with a gene on it, spotted onto it if you want to take it home with you. So this is no different than the 4-H club or the erector set in terms of understanding the components and building. And we know there will be higher level things that are built on top of each other.
Great, thank you.
So coming back to random versus non-random mutation, you'll have to excuse my ignorance in this field, but what is the source of randomness for the random mutation?
Random mutation, we have 3 billion GATs and Cs in a single set of chromosomes in a human. And every time a cell divides, when you're filled with gazillions of cells, it has to make an exact copy of that. And that exact copy is done by enzymes. And going from mother to child, there's about 100 errors made in that copying process. It's just a stochastic, as far as we can tell, almost random, a random event across the genome. And so these are just a single G or a single T or A or C is changed. And if it doesn't affect you functionally, you're fine. A simple arithmetic analysis says if there's 7 billion people on the planet, you have 3 billion bases of DNA, so there's more people than there's DNA, and everybody carries 100. That means 700 billion DNA sequence errors exist. So every possible mutation that you can live with exists already on this planet. We just have to sequence everybody to see what's there.
Yeah, but if the processes are purely mechanical or chemical, I don't see a source of randomness there.
The randomness is, you can make it less. You can make it more frequent with radiation and other things. It's the thermal inactivity. It's a misrecognition of the perfection. The idea is an enzyme is looking for a substrate, and apparently it gets it right 99.9% of the time in finding the right substrate.
And the nuance in your articles and your comment is important, because when you look at DNA, research by Ting Wu over at Harvard is showing that there are highly conserved sequences that are common to animals, that are common to humans, that are common to plants. So there are certain pathways, certain genes that are common across various species. It means if you get a random mutation in that, likely the animal dies or the plant dies. So some of the sources of randomness, if you get radiation, and the radiation hits and splits your DNA in a certain way. If a chemical comes in and splices your chemical in a different way, if the sun comes in, if alcohol comes in, if tobacco comes in, if coal smoke comes in. So there's a whole series of things that are trying to rip your DNA apart every day, and your DNA is continuously restitching and remaking itself, right? And in a bunch of these places, those cuts are at random. If they're cuts at random in the wrong place, the organism will die and not reproduce.
You get cancer, basically.
Yeah.
So if you look at the DNA as a closed system, there's no, what you're saying, there would be no sources of randomness in that case.
If it was 100% closed, but just a cosmic ray coming in, hitting the DNA, can actually cause a single base to change. and that has to be repaired, and if it's not repaired properly. And so the point of living to 100 is this is happening every day, every second in our bodies, in every single cell. We're trying to correct things. It is a very rare event for these mutations to arise because we have so many redundancies in the pathways, not wholly closed. Yeah.
So my question is, what sort of effects are humans having on the random mutation side of things? Do we see a change in random mutation rates? I could see things being radiation or hormones.
Well, that was a piece of the last century. I mean, we were not dummies when we figured out that asbestos, radioactivity, a lot of toxins, DDT, et cetera, were causing outbreaks of cancer and other diseases. And so they tended to be organ specific because the toxin would accumulate there, although with radiation, or it tended to be in cells that reproduce quickly because the DNA was being repaired all the time, or was more likely to be changing. And so those were where the cancers were coming up. In terms of being random, there's only one paper I know that says that there is something that about the process that is not random, and it has to do with some asymmetry about the enzymes. But in general, people have described it since the 1920s, and since, including Mendel's ideas of genetic units or genes, that these are just absolutely random processes.
Is the amount of, so you said 100
per generation. It ranges from 50 to 400 in different papers.
Going up or down?
Well, that's a new paper that just came out a couple months ago from David Wright, because that's how we do our genetic clocks of how long ago we separated from apes, is based on how many mutations they have relative to us. Now, if the clock was 400 per generation, it's a different time period versus 100. So right now, the operating number is 100 until we get more data.
This talk started out by emphasizing that mutation is a very important part of evolution, essential. I may have some sort of genetic mutation that has led me to be in favor of nuclear energy. So I want to ask a question about radioactivity, ionizing radiation, and that is that life has evolved bathed in radioactivity for billions of years, and therefore, one, life is very resistant to it. We have all these mechanisms that are self-correcting, all this error correction that you mentioned. And also, it seems like without all that ionizing radiation, evolution certainly wouldn't have proceeded as quickly as it had. Mm-hmm. Does that sound right?
That's right. I mean, the Earth is a relatively protected environment. Life first arose in water, where you actually have more protection, and there are enzymes that actually repair and prevent. It's actually an oxidizing reaction that is a result of radiation that actually breaks the DNA and causes the problem. So we have lots of dealing with oxygen as well as radiation has been something we've worked against. There is a species of bacteria called I forgot the radians, which actually can handle a million-fold more radioactivity exposure than we can, simply by revving up all of these mechanisms. And so there's a yin and yang play about we need to adapt to the current environment. If the environment's changing, we actually rev up these systems to repair and to proliferate as a species, or any species.
And we are unfortunately out of time. So what we'd like to do is just, this is something for all of you to think about. This is one of the most exciting areas sitting out there. There are very few adventures that are as important and will change the world as much as understanding life code. So have fun with it, guide it, help us, debate it. That's partly why we wrote this book.
One brief comment, you don't need to know any biology to read this book, by the way. It was written for my kids and my wife, as well as for Juan's kids and his wife.
Thank you all very much.